When World War II finally came to a close, British military leadership took a long, hard look at the true state of the Royal Air Force. Overall, the picture didn't look half bad, and the fleet seemed reasonably capable. But there was one glaring weakness that stood out, even without a deep technical dive. The state of Britain's long-range bomber force was passable for 1945, but it desperately needed an urgent overhaul. The main striking power of RAF Bomber Command still relied heavily on the Lancaster and Halifax, but the harsh reality was that by then they were hopelessly obsolete. Their airframes had completely maxed out their development potential. Things weren't helped by the supposedly brand-new Avro Lincolns, which started entering service in the summer of that same year. Under the skin, these were really just slightly upgraded Lancasters. They were practically obsolete the second they hit the flight line. Relying on overseas help was also a pipe dream. The British wouldn't get their hands on modern American bombers like the B-29 until the early 1950s. And it came at a steep political and financial cost. On top of all that, there was a massive paradigm shift happening. The aviation industry was rapidly moving into the jet age. The era of the piston-powered bomber was inevitably coming to an end. Furthermore, Great Britain firmly decided it needed an independent nuclear deterrent, completely separate from the Americans. The British atomic bombs were still just on the drawing board back then, but they had every reason to believe they could build them in short order. And at the time, the only reliable way to deliver that kind of devastating payload over enemy territory was with a heavy bomber. The Air Ministry fully understood these challenges and immediately started looking for a solution. By early 1946, the military had drafted a strict operational requirement for a clean-sheet jet bomber, purpose-built to carry a nuclear weapon. According to their specs, this future weapon would weigh exactly 10,000 pounds, measure about 30 feet long, and have a diameter of almost 10 feet. The new aircraft needed to carry this massive payload over a combat radius of 2,000 nautical miles. On top of that, to successfully penetrate enemy airspace, the bomber had to cruise at a staggering 575 miles per hour, at altitudes between 40,000 and 50,000 feet. Once the engineers started crunching the numbers, one thing became painfully obvious. Building an aircraft like this was technically feasible, sure, but it would take a massive amount of time and an absolutely astronomical budget. Even worse, just to hit those performance targets, the designers would have to rely on unproven, bleeding-edge technologies. This drastically increased the risk of the entire program failing. Critics across the industry were calling for the Air Ministry to dial back their expectations and make the bomber's requirements a bit more realistic. But the British brass dug their heels in and refused to back down. In the fall of 1946, they issued an updated specification that was practically identical to their original, wildly ambitious concept. And by early January 1947, those exacting requirements were officially set in stone. According to the final requirements, the future bomber had to meet the following specs: the ability to carry a 10,000-pound atomic bomb, a combat radius of 1,500 nautical miles with a maximum ferry range of 3,350 nautical miles, a cruising speed of roughly 575 miles per hour at operating altitudes between 35,000 and 50,000 feet. Down low, the speed requirement was simple but brutal, as fast as absolutely possible. Finally, the aircraft had to be packed with the most advanced navigation and electronic warfare suites available. That same day, this incredibly complex technical challenge was issued to leading British aircraft manufacturers Handley Page and Armstrong Whitworth. The very next day, 3 more industry giants received identical classified data packages. These were Avro, Bristol, and Short Brothers. A few days later, English Electric joined the race. By the end of January, most of the companies officially announced they were ready to bid on this unprecedented contract. This included Avro, Armstrong Whitworth, English Electric, and Handley Page. Ultimately, it is safe to say this intense workload and fierce competition paid off in a huge way. In the early 50s, the world was introduced to the legendary British WWII bombers. These included the Vickers Valiant, the Handley Page Victor, and the famous Avro Vulcan. But today, our story takes a completely different path. Short Brothers declined to bid under the military's initial, extremely strict requirements, but they kept the lines of communication open. As it turned out, that was a smart move. Just a few days later, the Air Ministry issued a new requirement, This was a backup bomber project. It was essentially an insurance policy, just in case the more ambitious and complex designs fell through. This time around, the customers scaled back their expectations significantly. This made the requirements for the future bomber much more realistic. Now, the aircraft was expected to hit a top speed of nearly 500 miles per hour. It also needed an operational ceiling just under 45,000 feet. On top of that, the military dropped the strict engine-out takeoff requirement. Overall takeoff and landing specs were also relaxed. However, a new, critical constraint came into play. The bomber had to operate seamlessly from standard, pre-existing military air bases. This rule automatically limited the aircraft's maximum takeoff weight. It had to be somewhere between 121,000 and 139,000 pounds. The design that Short's engineers finally brought to the table looked like a classic four-engine, straight-wing aircraft. The heart of the bomber would be the latest turbojet engines from Rolls-Royce. This was the AJ65, which would later become famous as the Rolls-Royce Avon. Each of these engines produced roughly 6,500 pounds of thrust. Interestingly, the designers initially looked at 3 different engine mounting configurations. Their favorite approach was to house them inside paired nacelles, cleanly mounted under the wings. But after further aerodynamic testing, they had to scrap that idea. In the summer of 1947, the engineering team came up with a highly unconventional solution. They essentially rotated these twin engine pods vertically, so one engine sat flush on top of the wing and the other hung symmetrically right below it. The design team was genuinely convinced that this vertically stacked layout would be perfect for high subsonic flight, even though it looked a bit odd at first glance. This clever design choice reduced aerodynamic interference and saved structural weight. Plus, it improved the aircraft's overall aerodynamics and provided much cleaner airflow directly into the engine intakes. However, the military didn't stop tweaking their wish list. At their next meeting, they proposed even more radical changes to push the design further. They wanted the engineers to switch to a swept wing with 20 to 25 degrees of sweep. They also wanted to install significantly more powerful Napier engines. But the team at Short stood their ground and defended their initial vision. They successfully convinced the top brass not to overcomplicate the design. In the end, the military officially approved the final spec. This almost entirely matched the bomber's original, simpler concept. After that, Shorts got the green light and an official contract to build 2 complete SA.4 aircraft. The plan also called for a third airframe built strictly for static testing. Originally, these brand new bombers were supposed to roll out of the Belfast factory in early 1949. But in reality, the timeline for the SA.4 completely fell apart, and there were a few major reasons why. First off, the SA.4 was one of the first British aircraft to feature a cutting-edge hydraulic flight control system. Since their engineers didn't have much experience with mechanisms this complex, they had to build a dedicated flying testbed. To do this, they took a standard Sunderland Mark V flying boat and heavily modified it. They installed the exact same elevator and rudder controls destined for the new bomber. They only started prepping this testbed for trials in the summer of 1949. This was right when the first SA-4s were supposed to be taking to the skies. The actual flight tests dragged on all the way into the spring of 1951. Sure, using the Sunderland allowed them to safely tweak and calibrate the new hydraulics in flight. On top of that, an hour of flight time on the old seaplane was a fraction of the cost of flying an experimental SA-4. But all of this took a heavy toll on the overall project schedule. The second big problem was the engines themselves. It turned out that Rolls-Royce simply couldn't deliver the promised high-performance RA3 engines for the first SA-4 prototype in time. The designers had to scramble and install weaker Avon RA2 engines instead. These only put out 6,000 pounds of thrust rather than the planned 6,500. But the worst part was that these temporary engines had a different footprint. This was because of a built-in electric starter. Because of this unexpected detail, the engineers had to completely redraw the blueprints and redesign the engine nacelles. And finally, construction was seriously delayed by a purely practical issue. The order for this ambitious bomber landed at Shorts at the worst possible time. It happened right when the company was in the middle of a massive relocation from Rochester to a huge new production facility in Belfast. But the biggest problem for this bomber came from a totally different direction. it suddenly became clear that the need for the Sperrin, which was the official name given to the SA-4, was rapidly vanishing. In reality, this project had always been intended strictly as an insurance policy. Military command wanted a backup plan just in case they ran into major issues developing their primary strategic bombers. But as it turned out, development on those frontline bombers was going incredibly well. This proved fatal for the short bomber. In March 1950, the military officially announced that they simply didn't need the aircraft anymore. However, the designers weren't about to give up without a fight. After a few months of intense negotiations, they finally reached a compromise on October 12th. It was decided that they would finish building the 2 airframes that were already on order, but they were reassigned to a completely different role. From then on, they would serve exclusively as experimental flying testbeds. In early 1951, the first Sperrin prototype officially rolled off the assembly line at the Belfast plant. But the celebration was short-lived as an unexpected logistical headache emerged almost immediately. It turned out that the runway at the Sydenham factory airfield was just too short for such a large and heavy bomber. To actually begin proper flight testing, engineers had to partially disassemble the brand new aircraft. They then carefully transported it by road to the Aldergrove Military Air Base, located about 12 miles away from the factory. The long-awaited day finally arrived. On August 6, 1951, the first Sperrin proudly rolled out onto the runway. Over the next few days, the crew ran thorough ground checks. They also conducted high-speed taxi tests. During one of these runs on August 9th, the bomber actually lifted off for a split second. It hopped down the runway for about 240 feet. The engineering team successfully tested the drogue parachute system right then, too. It was not without a few minor hiccups, though. During these tests, the skin on the elevator was accidentally damaged. The ground crew spent almost a full day working hard on repairs, but by the evening of August 10th, the bomber was completely prepped for its first official flight. Everything started with a final taxi run. After that, they topped off the fuel tanks. At 8:18 p.m., the aircraft lifted off. It was heading out on its historic first flight. Short's chief test pilot, Thomas Brooks Smith, was at the controls. His SA-4 smoothly climbed into the sky at an airspeed of around 140 miles per hour. It used up just 1,200 feet of runway for the takeoff roll. This maiden flight lasted 24 minutes. It went flawlessly without a single technical glitch. Before long, the flight test program had to be temporarily put on hold. Management decided to show off their pride and joy to the general public. This took place at the prestigious Farnborough Air Show in mid-September. After a triumphant return to Aldergrove, test flights kicked back into high gear. Experienced test pilots Thomas Brooks Smith and Walter Runciman took turns in the cockpit. Eventually, all testing was moved back to the Sydenham factory airfield. The company had even invested heavily in extending their runway just to make this happen. In the air, the bomber performed flawlessly. It had excellent flight characteristics. It proved to be a forgiving and highly responsive aircraft to fly. Interestingly, rigorous static structural tests were only carried out a few months later. This was after the SA-4 had already started regular flight operations. The results were impressive. The wings only started to fail when the load hit 104% of the maximum design limit. The rugged fuselage held up to an incredible 108%. In the summer of 1952, the aircraft finally received its intended Avon RA-3 turbojets. This meant engineers had to redesign the engine nacelles once again to accommodate the new dimensions. During the very first test flight with the upgraded power plants, the crew ran into a serious issue. They were cruising at 42,000 feet and a speed of Mach 0.85. Suddenly, the ailerons began vibrating violently. This is a dangerous aerodynamic condition known as flutter. Luckily, the highly trained crew kept their cool. They reduced airspeed and safely recovered the bomber back at the airfield. The resulting damage turned out to be surprisingly minor. To prevent similar issues down the line, air deflectors were installed between the exhaust nozzles. On top of that, small aerodynamic strips were added to the wing's trailing edge. Their actual benefit was pretty questionable, though. Because of this, they were removed after just a few flights. From there, the testing program proceeded slowly and methodically. In May 1953, the aircraft was once again the star of the Farnborough Air Show. This time around, it showcased a brand new radar. It also featured a highly accurate radar bombsight system. Both were developed specifically for the upcoming generation of British V bombers. It was not until January 1954 that the lengthy flight test program officially wrapped up. So what happened to that first prototype? It was immediately sent back to the engineers at Shorts. There, it was completely converted into a flying testbed for evaluating the latest jet engines. On July 5, 1955, the modified aircraft took off from RAF Aldergrove. For this flight, one of its engines, specifically the lower left one, had been swapped out for the brand new de Havilland Gyron turbojet, the DGY-1 model. It produced just over 15,000 pounds of thrust, just to give you an idea of the sheer scale. That was only slightly less than the combined thrust of the Sperrin's 3 other engines. At the controls for these critical tests were 2 veteran aviators, Short's test pilot Jock Easy and de Havilland's chief test pilot Chris Beaumont. The test turned out to be highly successful. By August 4th, the aircraft was ferried over to the engine manufacturer's factory airfield. Then, in early December, the airplane returned. But this time it was sporting 2 even more powerful DGY-2 turbojets. They were installed in place of the original lower Avon engines. Each of these massive new power plants delivered over 20,000 pounds of thrust. Thanks to this upgrade, the Sperrin's total thrust-to-weight ratio more than doubled compared to its original configuration. Preparations for the next stage of testing moved pretty slowly. In its new, much more powerful configuration, the bomber finally took to the skies again on June 26, 1956. The flight was not without a little drama either. During the sortie, the aircraft lost one of its main landing gear doors, dropping it right into the ocean. To fix the airplane quickly, mechanics had to cannibalize the needed part from the second, mothballed Sperrin airframe. Later that same year, in 1956, this first prototype made its final appearance at the Farnborough Air Show. From there on out, its career continued strictly as a flying testbed. After the Gyron engine program wrapped up, the aircraft spent a few more years flying all sorts of research missions. Eventually, the airframe was permanently grounded and put into storage. By the mid-60s, the first experimental Sperrin was quietly scrapped. As for the second Sperrin prototype, it made its first flight from Aldergrove on August 12, 1952. Unlike its predecessor, this aircraft was fitted from the start with the more powerful Avon RA-3 engines. They produced roughly 6,500 pounds of thrust. These were actually the engines originally intended for the short SA.4 bomber series. However, this particular airframe did not have a radar system installed, so instead of a standard radome, it was fitted with a duralumin nose cone. This cone had a slightly different shape. It was also missing some of the other standard production equipment. By the time construction on this second prototype was completed, it was absolutely clear. Its only real future was serving as a flying testbed for new weapon systems. Because of this, the bomber was equipped with a fully functional bomb bay and specialized gear to carry nuclear weapons. In late 1952, the aircraft was handed over to a top-secret unit. This unit handled instrument and weapon testing at RAF Martlesham Heath. At first, it was based at RAF Woodbridge. There, it played a major role in what was known as the Woodbridge Project. This was a highly classified program aimed at developing and testing the British nuclear bomb. It went by the rather romantic name Blue Danube. The aircraft repeatedly dropped exact ballistic mock-ups of the weapon over the test range. Throughout these intense trials, the manufacturer, Short, essentially leased its flight crews and entire maintenance team to the Royal Air Force. Once the nuclear testing wrapped up, the second prototype was put to work testing other cutting-edge weaponry. This included the Blue Boar guided bomb. It featured a television guidance system that was completely revolutionary for its time. But the era of these aircraft was fading fast. On July 3, 1956, this second aircraft took to the skies for its final flight. It flew back to the Short factory airfield in Belfast, where it was permanently grounded. For a while, the airframe just sat in a hangar. It served as a parts donor for the first prototype after it suffered landing gear damage. Ultimately, on June 2, 1958, this unique aircraft was scrapped as well. The story of the Short SA.4 Sperrin, despite its unassuming looks, is a prime example of the pragmatic approach the British military took when developing new aircraft. After ordering a whole series of revolutionary V bombers, the British decided to hedge their bets. They didn't want to risk everything, so they greenlit another, much more traditional and conservative design. The idea was simple. If those cutting-edge projects ran into technical trouble, the country wouldn't be stuck relying solely on aging World War II-era bombers. As it turned out, those fears were unfounded. British industry proved it was more than capable of rolling out state-of-the-art aircraft quickly and reliably. But even when the Sperrin was no longer needed for frontline combat duties, it wasn't just thrown away. The completed airframes found their true calling. They were put to heavy use as flying test beds for a wide range of crucial flight tests. So let's take a closer look at the design. Structurally, the short SA.4 Sperrin featured a classic high-wing design with a straight wing and a conventional tail section with a single tail fin. Most of the airframe was built out of high-strength aluminum alloy. This made the bomber both sturdy and relatively lightweight. The wing featured a symmetrical airfoil and was built around a two-spar structure. Engineers set the angle of incidence at 4.5 degrees. The dihedral was just a single degree. Along the leading edge, the wing had a sweep of 16 degrees. The fuselage was divided into 3 main sections. Up front was the pressurized crew cabin and a dedicated station for the bombardier. To reach that station from the main flight deck, a crew member actually had to crawl through a purpose-built tunnel. The nose section also housed the radio equipment bay, concealing the navigation and targeting radar. Between the cockpit and the forward fuel tank, engineers included a stowage compartment for survival gear. Among other things, this held an inflatable life raft in case the crew ever had to ditch. The center fuselage was dominated by a massive bomb bay. It measured just over 30 feet long. It had a total volume of more than 3,200 cubic feet. The bomb bay doors were hydraulically actuated. Out back, there was a pretty interesting design quirk in the tail section. To prevent hot jet exhaust from damaging the horizontal stabilizer, designers mounted it with 3 degrees of dihedral. The bomber's landing gear was developed by British Messier. It featured a tricycle configuration with a twin-wheel nose gear and 2 main gear assemblies. This gave it a track width of over 32 feet. After takeoff, the nose gear retracted aft into a dedicated bay right under the cockpit. The main gear used heavy-duty 4-wheel bogies that retracted inward into the wings. The entire system was hydraulic. For safer landings, the main wheels were equipped with Dunlop anti-lock brakes. To help the aircraft decelerate after touchdown, it was also fitted with a drag chute. This was stowed at the extreme rear of the fuselage, right at the base of the vertical stabilizer. The heart of the short Sperrin was its 4 non-afterburning Rolls-Royce Avon turbojets. Each put out about 6,500 pounds of thrust. The engine layout was highly unusual. They were paired up in vertically stacked nacelles built directly into the wings. This meant one engine sat above the wing line and the other right below it. The fuel system was massive. It utilized 8 tanks in the fuselage and another 14 across the wings. This brought the total capacity to nearly 7,500 gallons. Because fuel burn constantly shifts the center of gravity of the aircraft during a long flight, engineers installed an automatic fuel management system. It continuously transferred fuel between tanks to keep the bomber perfectly balanced in the air. The aircraft carried a 5-man crew. This included 2 pilots, a bombardier, a navigator, and a radio operator. They all worked together in a single pressurized cabin. Interestingly, during a bomb run, the bombardier had to leave his regular seat. He then had to crawl into a cramped, dedicated station right in the extreme nose of the bomber. The pilot sat facing forward while the other 3 crew members faced aft. When it came to crew survival, only the pilot in command got a proper ejection seat. In an emergency, everyone else would have had to bail out manually through a ventral escape hatch. To keep the crew conscious at high altitudes, the cabin maintained a pressure altitude of about 8,000 feet. This pressure was provided by engine bleed air. The bomber also featured a robust oxygen system. It was fed by 7 cylinders stowed just below and forward of the cockpit. This aircraft could carry a massive arsenal inside its internal bomb bay. It was rated for up to 20,000 pounds of conventional ordnance. It was also fully capable of delivering nuclear payloads. To guarantee pinpoint accuracy over the target, the bomber relied on a radar bomb sight. Interestingly, the Sperrin bomber carried absolutely no conventional defensive armament. like cannons or machine guns. Its only line of defense was supposed to be a dedicated electronic warfare suite to jam enemy radar. In practice, however, not a single aircraft ever actually received the promised system.